Yeah, thanks to Arnab specifically for inviting me and organizing this conference. And thanks to all of you for being in the audience. So I'll be talking about quantum matter in equilibrium for a change. And I'll only talk about the ground state even then. But I hope that you still find it interesting. So first of all, I should say that this work was done with an extremely bright, motivated, and hardworking undergraduate intern who was in the audience, and she played a major role in moving this project forward. We are still writing it up, so any comments and questions at this stage are particularly useful. So roughly, the problem that I'm going to talk about is I'll imagine spins sitting at the nodes of a complex network. So each bond in the network represents some antiferromagnetic coupling between the spins. And I'll assume that each bond has the same antiferromagnetic coupling. So each bond is trying to anti-align the spins that it is connected to. But of course, it's a general network, so there will be frustration. You cannot satisfy all the bonds. And so then the question is, what determines the ground state magnetization? Or just to ask one question. Here, so how does the network topology determine the magnetization of the ground state? And this is an attempt to visualize the ground state using color. So the blue here is supposed to represent that that bond is closer to a triplet, and the red denotes that bond is closer to a singlet, and so on. So just by looking at these two figures, you can see that depending on the network, you'll get very different ordering in the ground state. And that's what I'll be talking about. Yeah, so it's a bit of an open-ended question, but I'll try to give specific graph structures which are important in determining the magnetization. Okay, let me give you the main punchline straight away. So it turns out that it is the heterogeneity of the network as determined by the number of neighbors of different nodes, a certain type of heterogeneity. That turns out to be the important, crucial factor for determining the net magnetization, not the level of frustration in the network, which might be a bit counterintuitive. Okay, and those of you who listened to a version of this talk 2 months ago, then there will be some interesting updates. All right, so the whole project is really an attempt to explore many-body physics outside of regular lattices. So condensed matter physics, most of what we are taught is formulated on regular lattices, but there's no fundamental reason from a many-body physics perspective to be limited to regular lattices. And it could be that if you allow more general connectivity between the interacting units, you are likely to get more exotic behaviors. And this is sort of motivated in part by classical network science, where we know that the network structure can give rise to novel phenomena, and it can control network topology, can have a large influence on disease spreading and information spreading and so on. Okay, and not only that, nowadays it's possible to synthesize almost arbitrary network of interacting spins in controllable platforms. So Pedram's talk gave sort of a flavor of this, in which he was talking about superconducting qubits, which are capacitively coupled, which is like a spin exchange interaction in the two qubits. And there are also other platforms that people have suggested, and these are review articles summarizing the advances. Okay, and so why magnetism specifically on networks? It's interesting in the context of magnetism because going to a general network means that you can basically tune the level of geometric frustration in your network, and that can have a large impact on magnetic properties. So as I said, I'll be considering equal strength antiferromagnetic coupling. In the general case, you'll also have a positive constant Gij in front, which I'll ignore because I only want to focus on the effect of the structural properties and not on the coupling constants. Okay, and so if you have such a model and if you have a regular bipartite lattice, like a square lattice, then of course there's no problem in satisfying all the bonds. You can just put in up-down in anti-parallel way, and you get an antiferromagnetic ground state with total spin 0. Now there's a large body of literature looking at these frustrated systems in the context of regular but non-bipartite lattices, such as a Kagome lattice, in which it is known that the interplay of this geometric frustration, so frustration meaning that if you have triangles like this, I can assign up here, down here, then I don't know what to do with this thing, because I cannot satisfy both these upper bonds. And the interplay of this geometric frustration and interactions in the system is known to give rise to exotic orders such as spin liquids. So in this case, the network is frustrated. The total spin turns out to be 0 if you have an even number of sites. I'll only consider spin halves. But you may not have long range order. It could be fluctuating spin singlets forming a spin liquid, for example. Now, if you go to the non-bipartite case, again, general networks, again, the bipartite case is easy to understand. Here again, you'll have only bonds between some A sublattice and some B sublattice, and it's possible to get some net non-zero magnetization if there is a sublattice imbalance between A and B. Okay, so this is not very complicated, but if you go to general non-bipartite networks, then very little is known about what is the collective behavior of such networks. It's going to be frustrated because there will be triangles and pentagons and so on. So we don't know generally what happens to the total magnetization, S total. I have SU2 symmetry in the problem, so this is a good quantum number. And even less is known about what happens to the ordering, what is the actual ground state order. And so the question is, how does the network topology in the general case determine the magnetic order in the ground state? Right? And it turns out that the magnetic order question is too open and a question to tackle in one project. So here I'll just limit myself to talk about what determines the net magnetization quantum number S total. I'll not talk about anything about the structural properties. By topology, I mean the entire connectivity of the network. So the bond distance, you mean? Yeah. So all the bond strengths are the same. All right. So the first natural place to start looking at is random graphs, which are also called Erdős-Renyi graph, with a given number of sites, n, and a given number of bonds, ne. And here you see 3 sample graphs with increasing number of bonds with the same number of sites. And so as I increase ne, keeping n the same, I increase the average number of neighbors per node. This is not the same for all the vertices, but the average number increases with ne linearly. And so if you generate ensembles of such graphs and calculate S total numerically, and then you'll get some total spin distribution in these different ensembles for different values of ne. This is how they look like. So you notice 2 things. One is, so this is, I've tried to show the entire range of possible S total values, which basically goes from 0 to n by 2. But here it's mostly concentrated in the left corner, so the magnetization is small, which is not very surprising because I have antiferromagnetic interactions. But you also see that as I increase ne, that it becomes more and more smaller, so it sort of falls. If you plotted the average value of the S total as a function of the average number of neighbors, it's also called a degree, then it falls monotonically. And we can understand the limiting cases of very small and very large number of bonds. So the minimum number of bonds that you need to keep a graph connected is n-1, in which case you just get trees like this. And a tree is again bipartite, so this is a easily solvable problem. You assign A and B levels, count the difference, you can have a non-zero magnetization if Na minus Nb is non-zero. Okay, so this turns out to follow a Poisson distribution, which in this case has an average close to 1. Okay, on the other hand, if I now keep increasing the number of bonds, the maximum I can get to is when I have all-to-all connectivity in the network, then the Hamiltonian is just S total squared, and so you minimize S total to 0 in the ground state. And so you see that it's expected that it'll fall from some average non-zero value to some 0 as I keep increasing the number of bonds. So this itself is not very surprising. But now we want to understand more about what structural properties of the graph are important, other than just the average number of neighbors. And there you start looking at correlations of S total with different structural properties of the graph. So these 3 curves are showing sort of 3 measures of frustration level in the graph, if you like. So this frustration index NF is defined to be the number of bonds, the minimum number of bonds that you need to cut in order to make it bipartite, in order to kill all frustration. So this in the graph network community is taken as a measure of frustration, so a global measure. Number of triangles is a more local measure of frustration, and the average path length D means the average number of hops you need to make in order to go from any node to any other node. So if D is small, that means you can get to more nodes with a given number of hops. So a single spin can affect more spins up to a given order in the coupling. So that also adds to the level of frustration, if you like. This is sort of indirect way adding to the frustration. Now, if you see the correlation with S total, they are all falling close to this gray band, which is supposed to denote the area of statistical insignificance. Okay, so if any dot for the sample size we have, which is close to 1,000, falls within this gray band, you would say that it's consistent with having no correlation with S total at all. And here you see that all these measures of frustration, the points are lying either inside or close to this gray band, which means that the level of frustration has very little correlation with the net magnetization, okay, or weak correlation at most. Now, if you, two other things it turns out has a much stronger correlation. One is the heterogeneity that I mentioned at the beginning. So this is the spread in the number of neighbors or degree in the graph, which is denoted by delta k, some root mean square deviation, which has a net positive correlation, which means that the graphs which have higher spread also tends to have higher level of magnetization. And there's another thing which is called the assortativity A, and this is sort of like the degree-degree correlation. So if you, a positive value of A means that high-degree nodes are connected to other high-degree nodes, low-degree nodes are connected to other low-degree nodes. Whereas if I have a negative value of A, that would mean high-degree nodes are connected to low-degree nodes. Okay, so that would mean a big degree mismatch across the bonds that actually can lead to large magnetization. So here you see a negative correlation. So it means the more negative A is, that's correlated to having a higher value of magnetization. Okay, so these are the main things you notice, but this is of course in the family of random graphs. So you'd want to systematically vary these measures and see whether you can reproducibly observe these effects in different graphs. And that's what I'll go through in the next slides. So first, let's come to the measure of heterogeneity. So we can kill all heterogeneity in the graph by requiring every node to have the same number of neighbors, okay, just like in a square lattice. But if you only impose that constraint, you end up with what are called random regular graphs. So here you see it's not a regular graph, but every node has 3 neighbors in this case. So k is 3, there's no delta k. Okay, so then again, if you plot a distribution of spins in the ground state, you see remarkably that everything is at 0. So this is even number of spins, and everything is sitting at 0. So essentially, no graph with non-zero magnetization in this family, which strongly suggests that non-zero S total requires generically a spread in degree. So if you kill that spread, you kill non-zero magnetization. Okay, now in the previous slide, we decreased heterogeneity. Now you can also increase heterogeneity by going to what are called scale-free graphs. So people have suggested forming these graphs in this way. So this is a growth model where you're growing the graph by adding new nodes one by one. Each new node you add, you connect to a given number of existing nodes, but you do it with a preferential attachment. So that means the nodes that already have more neighbors are more likely to get one more neighbor as you connect the new node. Okay, and at the end, the family of graphs that you end up with has this power law degree distribution. That's why it's called scale-free. And it necessarily, this fat tail here means that some nodes end up with very large number of neighbors, right? And so these are called hubs. Some of these hubs you can see in this plot. So this is enhancing the heterogeneity in the problem, and these hubs will turn out to play a crucial role as far as the net magnetization is concerned. If you plot the spin distribution, you see that if you remember the previous histograms, this is now spread out to larger values of S total. This is possible to understand at the level of a single hub. If I had a single hub like this, a star, then of course I had assigned some upspin here and downspin, so I'll align all the outer nodes opposite to the hub node, which will give me a large S total. So this sort of explains why having these hub structures can give you large magnetization. Okay, so this is the summary of the heterogeneity case. As you increase the heterogeneity in going through these families, you end up with larger and larger average S total in the problem. Okay. The other result was that the relative insensitivity of the magnetization level to the level of frustration in the graph. Okay, so I should first say that this may be a little counterintuitive, because you might say that if I have more frustration, I cannot satisfy all the bonds, so maybe I get larger S total. But actually, from regular graphs, for example, if I have a Kagome lattice, there I have frustration, but S total is still 0. So from the study of regular graphs, frustration level doesn't really necessarily have a strong effect on the S total quantum number. It can have a large effect on the ordering. It can lead to spin liquids, but as far as the S total quantum number is concerned, it may not be important, which this study also shows. Okay, so the way we systematically vary the frustration level is you can remove all triangles. So you can generate random graphs without any triangles in them, and like in this plot, and you can see how this changes the spin distribution. So this was the spin distribution with triangles, without any constraint. And once you remove the triangles, you get essentially the same. So removing triangles from this family has almost no effect on S total distribution. Going to show the insensitivity again. Now, people have also come up ways for removing not just triangles, but short loops up to a given size. Okay, so this plot here is basically this second point in the yellow thing, where I've removed the minimum loop size is 4, so I've removed all triangles. Here I've removed all loops up to quadrilaterals, up to pentagons, up to hexagons, and so on. And so you see, as I remove more and more shorter loops, the magnetization eventually goes to 0. But it goes to 0 at a point which depends on the number of bonds, right? And just removing triangles doesn't really do much to it. It also doesn't depend on whether I'm removing even loops or odd loops. So again, going to show that it's not directly correlated with the level of frustration. Now it turns out that you can actually very readily reproduce these trends by just looking at the heterogeneity. So if you take the same ensembles and plotted the degree heterogeneity, you would get the same variation. So this trend is basically just following the trend in the heterogeneity, not the level of frustration, really. And so why this is going to 0 is that, so beyond this point, I cannot generate random graphs with these many sites and these many bonds, but without any heptagons or something. There doesn't exist any such graphs. So that's why there's no point beyond this. So if I took a point like that, it sort of looks like a random regular graph. So there's almost no spread in degree, and the magnetization is also very close to 0. So this is again going back, lending credence to the point that heterogeneity is the crucial thing, not the level of frustration. Okay, there is another way. So now this is a bit unsatisfactory because here I am removing loops in order to tune the level of frustration, but that is also changing the heterogeneity. Is there a way to keep the heterogeneity at the same level, but change the level of frustration and really isolate the effect of frustration? Right? Now, it turns out that there is a way to do that for at least a scale-free family of graphs. And so basically what you do is in the growth model, once you have connected a new node to an existing node, in the next step, you connect to a neighbor of the node that you just connected to, which gives rise to a triangle. Right? And so it turns out that this way you preserve the degree distribution, so preserve the heterogeneity level, but increase the number of triangles. Right? So this is two graphs with different values of this second step. This has fewer triangles, this is more triangles, both belonging to the same degree distribution family. And now if you plot what happens to the average S total as you increase the number of triangles, so here I'm plotting what's called the clustering, which is an absolute measure of the number of triangles. It goes from the minimum value of C bar is 0 and the maximum value is 1. And here we are able to tune over a relatively large range. But here you see the S total is almost, it's a weak variation. It's falling slowly, but not very strongly. Okay, so this again goes to show that the frustration level, if anything, has a weak effect on S total. Okay, the other measure, less familiar measure, it's called the assortativity, and we saw that in the full random graph family, this has a large negative correlation with S total. And so it turns out that you can also systematically vary the assortativity and see if you are able to reproduce this trend. The really nice thing about the study as a general comment is that people working on graphs have developed this very tunable way of varying the structural properties of graphs, and we can just use those methods and see the effect of those on the physics that we are studying. So that's a very nice thing. So the way you tune assortativity is what is called degree-preserving rewiring. So suppose you have a network, and I draw two bonds from the network, right? These are the two bonds between 1, 2, and 3, 4. Now, one is connected to other nodes as well, which are these dotted lines. Similarly, 2, 3, 4 are connected to other nodes. One has the most number of neighbors, is the highest degree. That's why the size of the point is bigger. And then I have then 3, then 2, then 4. Now, you rewire these two bonds in order to not change the degree, number of neighbors, but change the level of assortativity. So if you want to make it more disassortative, what you do is you connect the highest degree node with the lowest degree node and connect the remaining two. That gives you most disassortative. So this leads to a large degree mismatch across this bond. Whereas if you want to make it more assortative, then you connect the two higher degree nodes together and the two lower degree nodes together. This leads to more like connecting like type of thing. Okay, and so this way you can generate two graphs like this, which have the exact same degree sequence, degree distribution, but this one is highly disassortative, this one is highly assortative. And the way to see that is that this is a very structured graph where you see that this is connecting high degree nodes with low degree nodes, this part, and this is connecting the remaining mid degree nodes to each other. Whereas in the assortative case, you have high connecting with high in this part and low connecting with low in the remaining part. Okay, and so despite having the same degree sequence, this has a very large S total. This turns out to have an S total of 7, whereas this has an S total of 0. And we can sort of understand this by looking at this part again. So here you see that this is roughly bipartite. So this is A, these are B, this is A, and so on. And this has a large sublattice imbalance, so much fewer A nodes compared to B nodes. And therefore, that can give rise to some NA minus NB being large, can give rise to a large S total. So that is roughly the idea. And so this way you can tune the level of average assortativity starting from a random graph ensemble with Poisson degree distribution. As you vary the assortativity, you see a sharp change in the magnetization level going from a large value to almost 0. And the same trend is repeated for scale-free graphs, which have 1 by k cubed degree distribution. The only difference between the top panel and the right panel and the bottom panel is that the bottom panel is shifted to the right. It has a larger S total than the top panel because this has a larger heterogeneity compared to the top panel. Okay, so again, heterogeneity and assortativity, these are the two main things. All right, so it turns out that there's a nice way of putting these variations together and really be able to tune the entire S total distribution anywhere you like in the full range. So this is something, again, which was developed earlier as a model for the internet. It's called the copy model. It basically has 3 parameters. One is the number of spins, n. Then there's a parameter m, which basically is related to the average degree, average number of neighbors per site. And then there's a probability p, which is a tuning parameter, which controls the level of heterogeneity and assortativity in the network. Okay, so so this is if you want to know how it's generated. This tells you what it does. So basically, the punchline is that when p is 0, then you can basically get these embedded disassortative hubs in the networks that you generate. Okay, so disassortative because these are mostly connected to just low degree nodes, outer nodes, although there is some connectivity between them, so it's not bipartite or anything like that. But you get these embedded assortative hubs when p is 0. On the other hand, when p is 1, you just generate a random graph, the original graph that I showed before, which doesn't have such structure in it. So if you plot the level of heterogeneity, which is the spread in degree, as well as the assortativity, you see that both fall as a function of p. So as I increase p, it becomes less heterogeneous and sort of neutral assortative. So when p is small, it is highly disassortative, highly heterogeneous, and both of them go away as I increase p. And so if you look at the corresponding degree distribution, you see that the degree distribution of the spins sort of monotonically varies as I increase p from this point to that point. So this gives a way to generate a tunable spin distribution in these random graphs. Okay. Now, right, so this is another way of plotting it, plotting the average magnetization as a function of p, and you see that as I decrease the number of hubs or increase the number of neighbors, I reduce the magnetization level in the network. Okay, here's one slide on the structure of the ground state. So we haven't systematically explored the structure, but this is, if you take these hubbed networks and plot the spin-spin correlations, the blue line is showing that these two are close to a triplet, so they are close to being aligned, whereas the red ones are saying that they're close to being anti-aligned. So basically what is happening is that the hubs are getting aligned to each other opposite to all the outer nodes, which are aligned together. Okay, and so this difference, again, this is approximate bipartite kind of structure, imbalanced structure, which is what gives rise to a large S total. Okay, so the remaining 10 minutes, I just want to address the question. So suppose you are an experimentalist and suppose you want to create some general network in your lab and be able to tune the level of magnetization in the ground state, but you don't want to do it in a random way. Is there a way to systematically generate networks which are frustrated but still has a tunable value of net magnetization? Okay, and it turns out it is possible by going to a single hub. So if you have a single frustrated hub, which is like this, so the structure is that it has NC, in this case NC is 2, NC number of central spins, which are all-to-all connected together. The all-to-all part is not crucial, it's just something we took. And they are connected to these outer nodes, which are forming a Heisenberg ring, basically. So you have this wheel structure with this hub, the outer nodes, and the spokes connecting the hubs to the wheel. It has lots of triangles, so it's generally frustrated. And in this case, I allow the coupling strengths to also be tunable. So for example, I call the spokes to have a J, the central bonds to have JC, and the outer bonds to have JB. Suppose I can tune JB and JC. And the result is that by tuning these two JB by J and JC by J, you can basically tune S total. Okay, so this is the simple Hamiltonian. Some limits you can understand pretty easily. So for example, if I have JC is the strongest coupling scale, then the first term requires SC to be small. So if you have an even number of central hubs, you can make it 0. If SC is 0, then there is nothing at the center basically, so you just end up with the Heisenberg ring. Because the Heisenberg ring is antiferromagnetic, you want the total spin to be 0 in the Heisenberg ring as well. So you get SB equals 0 and S total is also 0. So you're gonna get a net S total equals 0 state. On the other hand, if you lower JC, you allow some net magnetization to persist in the central hub, and then it helps, so these spokes want a large spin in sitting at the outer ring, because that way, and sitting at the outer ring and anti-aligned with respect to the hub, that way you can lower the energy of these bonds. Whereas the Heisenberg ring itself wants an antiferromagnetic, so as the outer ring to be 0. Right? So there's a competition of these two terms, and so if JB is small, you get a large spin at the outer spins, resulting in a large value of S total. And so basically S total is tunable, you can show, by tuning these ratios between these two extreme values. Now it turns out that we don't have to guess because this is an exactly solvable problem. Both SB, the outer spin, SC, the central spin, as well as S total are good quantum numbers. And you can write the energy as a function of just SB and SC because they always have to be anti-aligned. So S total is basically determined once you have SB and SC. And the energy can be obtained from Bethe ansatz. So you can solve it exactly. And if you do, you get this kind of phase diagram. So this is the large JC case where the central spin is 0. Whereas, so this part is S total is 0. Whereas this part, when just JC is small, then the central spin is 1. I just have 2 spins at the center, so it can be either 0 or 1. If it is 1, then it turns out to be a competition of JB and J, and you get this staircase-like structure. As you increase JB, it sort of forces the outer spins to go to 0 eventually in steps. What's interesting is that the slope here diverges. So it goes from 0 to a macroscopic value at this point, and the slope diverges in the quantum case, but not in the classical case, because in the quantum case, SC cannot vary. In the classical case, because SC can also adjust, it doesn't diverge. Okay, so, all right, so, and you get a similar case where I have 3 spins at the center. Here you also get staircase-like structure because SC is non-zero here. So this is going a bit of a details. If not everything is clear, then it's fine. But the idea, the punchline is that in this network, it is possible to vary JB and JC in order to access the full range of magnetization across both continuous and discontinuous transitions. Okay. Right, so that's basically it. That brings me to the summary. So the main conclusion is that if you have such an exchange coupling mediated antiferromagnetic model, then the degree mismatch, the heterogeneity measured by these hubs, is what's important, not the frustration level, as far as the quantum number, net magnetization quantum number is concerned. But the open question, of course, is the structure of the ground state. Probably frustration will play a strong role in what is the actual structure of the state within the S total, given S total sector. It will be useful to have better analytical understanding of the importance of embedded hubs. Something I haven't mentioned is, of course, dynamics on these networks, which is a widely studied classical problem, but not quantum. And one interesting contrast is with kinetic magnetism. So instead of having exchange-mediated magnetism, if you have magnetism coming from the motion of doped carriers, then it turns out that, okay, so we have actually already started exploring that problem, and here frustration level turns out to be very important as far as the total magnetization level is concerned. This is with my postdoc Revati. So you see this sharp oscillation with the number of even nodes and odd nodes of the total magnetization S. Okay, so, and this is just to flash some of the other projects that are going on. So generating entanglement with local dissipative drive, getting global heating from local cooling, and understanding how different classical nonlinear phenomena can be understood from, as emerging from some underlying open quantum model. Okay, and I want to thank all my collaborators, including the ones mentioned here, who were involved in other projects recently, and also a special thanks to the MPIPKS HPC cluster, which was used extensively in the results. Okay, I'll leave you with the summary. Thank you very much.
Thank you. Questions? Yes.
So I'm a bit confused what you said about SC being able to vary in the classical case. Like, is it not a conserved quantity in that case?
It's also a conserved quantity in the classical case, but it's just that, the level of SC which minimizes the energy varies continuously as you change the parameters, whereas in the quantum case, they're quantized. So it's basically just the quantization is what's giving rise to the infinite slope in the quantum case. So this is just a consequence of the quantization. You can also solve the classical problem exactly with an ansatz. Yeah.
Okay.
Yeah, so this is a question about the degeneracy of the ground state. Is it always non-degenerate, or
yes,
spin glass-like behaviors?
Yeah, so we haven't explored that systematically. So most of the results I showed were obtained from DMRG. So the observation is that it always converges to a given value of integer value of S total, which probably signals that even if there are degeneracy, it's with a given sector of S total. So we don't expect degeneracy involving multiple different values of S total. But whether it's non-degenerate for a given S total or not, that we haven't really explored in detail. Some of it agrees with exact diagonalization for smaller systems, but we haven't explored that in detail.
Hello. I'm not sure if I'm asking the right question, but what if we have a random graph with random weights? Can we still
So as I said, we wanted to simplify the problem. So if you have random weights, there are the questions of disorder coming from the weights themselves, which we didn't want to get into. And so we didn't, we just said all the weights to be equal for all the random graph simulations.
Oh,
But that's a larger set of domains to explore. Yes.
thank you.
Are some of your results specific to the degree of locality of the Hamiltonian that you are considering?
What do you mean? So it's a general network, so and there's no bond length or anything. So I don't know what you mean by.
So there is no.
So there's no
second neighbor.
notion of locality in the general case, but of course you can define networks with some geographical constraints in it that we haven't explored.
I mean,
so
in the
that'll be more
regular network, you have the locality of the Hamiltonian, which is important for you, right? Like for example, on the Kagome, when you want to satisfy this totally equal to 0, you have strictly nearest neighbor Hamiltonian.
Yeah, so the here the neighbor is just defined by the bond. I guess one notion of locality will be the average path length between into arbitrary nodes in the network. So you can do the small world sort of this Watt-Strogatz network where you can tune the level of how quickly you can go from any node to any other node. That we have looked at, that doesn't have a strong influence on the level of S total.
Just one last question is so.
But it probably will have a large effect on the ordering. So whether it's spin liquid or that I agree.
So if you introduce more and more clicks in your graph.
More and
by
more?
clicks. So by click I mean simplexes which have all-to-all interactions. So for Kagome, a triangle is the simplest click.
Yeah.
So do you see some kind of transitions from an ordered state to a S total equal to 0 as a function of the doping of the clicks? Do you expect something to happen?
Yeah, so basically if you have some clicks, that they cancel each other out. So you get something, if you have some clicky region like this, they just locally cancel the total spin to 0, assuming all the bonds are equal strength. And then you're just left with the remaining one. That's the current picture at least. And the remaining one, if that itself leads to a large S total,
So I'm saying that if you now increase the number of the density of these clicks.
Yeah. So for example, in changing the assortativity, you go from a structure like this to a more clicky structure.
So, okay.
And here, so you see that so this is more hub-like, this is more click-like, and you see the magnetization going down. So I don't know if you're talking about phase transition specifically, that we haven't looked at because it's just random graphs.
Yeah.
But if you could have the same graph but tune the bond strengths or something like that to make it more clicky, you might get some phase transition.
Yeah, I mean, yeah, okay, yeah, sure.
Yeah, but this is just a level smooth crossover.
Yes.
I was wondering if, suppose there is a role of initial conditions. In case, suppose all the spins are aligned in this condition, and does it go to the same ground state or?
Yeah, it's an interesting, because here I don't have any SU2 breaking term. So if because S total is conserved, so if you started from a high energy sector, you will remain there. So if you want to add some inhomogeneity or some local magnetic fields in order to break the SU2 symmetry, in order to couple these two sectors, and if you have some phase transition, you have some way of growing to the other sector. But currently in the model, there's no such term.
If there is no questions, then let's thank all speakers this session.